Yeah. Good morning, students. Hello. Hello, students. Hello.
Yes, sir, you are audible.
Yeah. Yeah. So, yeah. So let's have any questions regarding the previous classes. So are you going through the textbook? So please do that. Otherwise, the whatever the content is, keep on the accumulating, and it will grow like anything, and later on you will feel difficulty. At least weekly once you can see what is happening, what was covered. Otherwise, the last moment when you try to look into the things contents, it will be very hard. So here, so can you see the slide now? It's a multiplication. Hello.
Yes, sir.
Yeah, right. Okay. So if you recollect, in the on Tuesday, we discussed about ALU, and so how to design the ALU, like for performing the multiple operations, like starting with addition, then afterwards adding, and then OR gates, right? Then how to use the adder for the purpose of subtraction. And using the subtraction operation, we can also perform the comparison, less than, set less than operation, and also the equality operation. So all of them we have seen in the last class. And the next one, today's lecture, we try to cover the other two operations, the known to be multiplication and division operations. So though the multiplication and division operations are not as frequent as addition subtraction, but we used to carry out this multiply and division operation during the normal the programs or a normal like application, various applications will come across this multiplication division, and we'll see that how this multiplication division are implemented in a processor at a very gross level or at a very superficial level. We'll see that if you can say that a flow chart level or like a block diagramic level and all. And then anyway, the internals of these things are again will be carried out by using adder circuits and all. We'll see that. So before going to that, you can see that the normal multiplication, the way we do in a conventionally during our elementary school, what we learned using a pen and paper will be something like this. You can see in the case of multiplication, you have there are three terms that are involved over here. One is the multiplicand and a multiplier, and then the result will be when you perform a multiplication between these two, the result will be placed in the product register, and all. The result is placed in the result will be there, final result will be there in the product register, and all. So the way we do the multiplication will be here. The multiplicand will be there, and then the multiplier will look at the the bits of the multiplicand or the digits of the multiplier, and then we'll perform the multiplication. We'll perform the multiplication with the multiplicand with the division each digit of the multiplier, and then we'll get the intermediate products and all. And then these intermediate products are properly shifted and then perform the addition. Then perform that. For example, here assume that 1000 is the multiplicand and the multiplier is something 1001. Here, for the sake of simplicity, we consider the decimal. These are the decimal numbers, but as if we place the decimal digits, decimal number such a way that which can also take care about the binary part also, like 0 ones. So therefore here when you do the multiplication with each digit of the multiplier, see that the leftmost digit is a 1. So therefore the multiplicand multiplied with this one, you will get 100. And afterwards the next digit is 0. So you multiply with that, you will get zeros. But you place this, the multiplicand here, the whatever the result of this part, the second intermediate result will be shifted towards towards left one place, and then again it's a 0. So you multiply, you'll get again a 0 sequence of zeros. Again you shift it by one more, and then the 1. So we'll get a 100. Then again shift it by 1, and these are these intermediate products. And then if you sum up all of them, then you will get the result. The desired the product and all, right? And for implementing this one, this kind of a multiplication here, we can use a straightforward way of implementation by using this particular block diagram and all. And here is nothing of block diagram, the hardware that is required to implement this particular multiplication and all, right? So here, if you look at here, the way the block diagram here is that, and here you can see here whatever the multiplicand here, that means each time whenever you multiply with the multiplier, the multiplicand will be shifted towards right. The multiplicand will be shifted towards right each time and all. So with that, what happens if you have whatever the multiplicand is there, that multiplicand each time you're shifting towards right. So therefore, when you look at all these partial products, all these intermediate products and all, so finally the multiplicand will reach to this one. That means to accommodate all these partial products, we need the space of twice the multiplicand size is required, right? So therefore here we'll use the register. Suppose we want to perform 32-bit multiplication, both multiplier and multiplicand are 32 bits. In that case, actually first initially the multiplicand will be placed in a 64-bit register, but the size of the multiplicand is 32 bits. So therefore we place the multiplicand in the left side of the in the right side of the rightmost place of the 64-bit register, and the remaining will be like filled up with the zeros. So that way you have 64-bit register. In that the multiplicand will be placed in the right side, in the rightmost side initially, and afterwards for every bit of the multiplier we'll shift the multiplicand. We'll shift the multiplicand and all, right? And and then afterwards, after shifting that one here for the sake of as we know, as a human we can able to perform all these four terms, we can able to add it directly, but as a machine cannot do it simultaneously. We'll do it like a step by step. That means for every time whatever the intermediate product will get, intermediate result you will get, all these intermediate results will be added like one by one immediately. So therefore here we'll use because this is a 64-bit one, so therefore we have a 64-bit ALU is required for performing the addition and all. And initially we'll keep a product will be 0, all zeros. Then afterwards we'll keep on add the product to the multiplicand, shifted version of the multiplicands from time to time. For every step we'll do that. And here the addition of multiplicand, that depends upon here the multiplier bits. If it is a multiplier bit equals to 1, then the shifted multiplicand will be added. If the multiplier bit equals to 0, we need not add also, but you have to shift the multiplicand, right? So that way you can able to like control these shifting of this multiplicand, adder, and this one yeah, these things you can able to do it by using a control circuitry. And here these controlling will be done based on the multiplier bit, if it is a 1 or 0, right? So that way, every time, and then here the multiplier bits also we had to see, like after looking at the first digit and all, then we had to see, check for the second digit, then third digit. Likewise, all multiplier digits also has to be visited. So based on every multiplier digit, the controller will make the action. Controller will take the action, whether what can be done, whether the addition has to be performed, or whether the list multiplicand has to be shifted. Each time it has to be shifted, whether it's a 1 or 0 and all. And if it is a 0, then there is no need to add, because even if you add all zeros also, the same result will be there. But if it is a 1, then you need to add the multiplicand, right? So you can see the sequence of steps in the performing the multiplication by using this particular circuitry will be this one. You can see this flow chart and all. Here, first we will start with the 0th multiplier bit and all, multiplier 0. If it is a 1 or 0, if it is a 1, multiplier bit equals to 1, it means that whatever the multiplicand is there, that multiplicand will be added to the product and all. Suppose if the multiplier is 0, then you need not add, because even if you add 0 also, there won't be any change in the product and all. So therefore you need not add, right? So the multiplicand, whenever the multiplier bit equals to 0, then you need to add. Then you need to add the multiplicand, a shifted version of multiplicand to the product and all. Then after you perform addition, that means the first bit and all, then what you need to do, then the shift the multiplicand register left. Shift the because for every multiplier bit, you need to shift the multiplicand to the left because it is originally placed in the right, left. And then afterwards, then they shift the multiplier bit towards right, because you need to check, you need to see what is the multiplier bit each time and all, right? First we are checking the 0th bit, then we will perform certain thing. We will perform whether it's a 0, whether the multiplier bit is 1 or 0. If it is a 1, you need to perform addition. If it is 0, then you need not perform addition, then go to the second, then go check the second multiplier bit. And again, so that way you need to check the each multiplier bit, and then you need to take the action whether the multiplicand will be added or not. And here each time the multiplicand will be shifted. Every time the multiplicand will be shifted. See that for every iteration the multiplicand will be shifted, and the multiplier bit also shifted towards right, so that you can able to come to know that what the multiplier bit will be. And based on the multiplier bit, we need to take the action and all. So that way here you can able to see the you can see. So for that reason, the here for the initial one, the very the basic circuitry where the multiplicand is required to be placed in 64-bit register, because the multiplicand will be shifted 32 times in the process of generating the final product and all. So, but the multiplier will be placed in the 32-bit register, and since the multiplicand will be there in the 64 bits, so therefore for performing the addition between the product and the multiplicand, we need to have 64-bit ALU is required. And anyway, the product will be, we know that suppose if the multiplicand and multiplier are 32 bits, then there is a possibility that the product will generate the 64 bits. 64 bits, and sometimes we'll have overflow will be there. So finally, to accommodate that, actually it requires 65 bits and all, right? But it's here, it's not shown here and all. 65 bits are required to take care about the overflow and sign bit and all, right? So now you can see the same thing here. Here this particular table, this shows the whatever the steps I have mentioned earlier. So the steps can be illustrated by observing the contents of this table, and because here the same steps whatever mentioned in this flow chart, whereas here this is for 32-bit. Here instead of 32 bits, here we mentioned with the 4 bits and all, because for the sake of simplicity, for illustration purpose, a 4-bit multiplier has been taken and a 4-bit multiplicand has been taken, and then we'll visualize that how the product can be generated and all. You can see that since it's a 4-bit and all, we need to have 4 iterations are required, because we need to check all the bits of a multiplier one by one, and then for every bit of a multiplier, then we need to shift the multiplicand also, and then we need to add to the product. We need to add to the product. So therefore, you can able to see that every step and all. First of all, you check. We need to check the initial values. That means the bit of a multiplier, of the least significant bit of a multiplier. Then based on that, whether the addition has to be performed or not. And here, since the least significant bit equals to 1, so therefore the multiplicand will be added to the product because the product is originally 0. This is your multiplicand because you see that the 4-bit multiplicand is placed in the rightmost position of the 8-bit register and all, because since it's a 4 bits, so we need to have a double the register is required because this entire multiplicand has to be shifted towards right at the end. So here one since it is a 1, so therefore the multiplicand will be added to the product. So we'll get the intermediate product will be this one, and then the shift then afterwards after happen this one, then you shift the multiplicand and shift the multiplier. Then when you shift the multiplier, then what happens? This the rightmost digit will go out, and then the next place will come into the least significant position. So this is observed. Now based on that, you need to take the next step. And here it's a 1. So therefore again the multiplicand has to be added. So the multiplicand is already shifted here. So therefore this is 100, and the product is this one. And now we add this product to this shifted version of multiplicand. You will get this is the result and all. And then afterwards again you just check you just shift the multiplicand and multiplier, then the multiplier will be 0. So therefore that means that actually here you need to shift the multiplicand, but you need not the addition need not be carried out, right? Because anyway we can add it also, I can perform addition also. So that way the remaining 2 shifts you can do it, but in the remaining 2 shifts the multiplier the left rightmost digit is 0. So therefore you need not perform addition because the same thing will be result. So you can see finally after the 4 rounds, 4 iterations, you can able to see that the product will be like this one, and the multiplicand will be reached to this position, to the rightmost position. So this way you can able to do that. This is just simply the true way of the way we do the conventionally. How do we implement in the by using the hardware components, the way we can do it. But here you can able to optimize this one. When you look at this, the way of when you're doing this conventional way of doing this one, conventional way of performing this multiplication addition or this multiplication. Here, even though we are using the 64 bits, but each time we are performing the addition with only 4 bits only. You can able to perform addition with 4 bits only, strictly speaking. Because here at the first time when you perform addition, so these 4 bits will participate of the multiplicand, and then the initial product will be very zeros. So therefore 00 and 100 will be added. Then afterwards, the next addition will be carried out will be like the shifted version of this one. Like you can see that actually here, whatever this that means the product can be shifted so that you can have 0, 100, and that will be added to the next multiplier, that will be 0. And likewise, you can able to see that instead of that means even though you are adding multiplicand all the time, you are adding a multiplicand of only those 4 bits. Only 4 bits of multiplicand will be added. And similarly, the product also, you can see that only that 4 bits will be carried out, the addition will be carried out. And but finally, at the end, you can able to get the result of product will be like 64 bits. But so by viewing this one each time, but even though you are using 64 bits, but out of that only the 4 bits are only participated in addition over here, and similarly here also. So therefore, we can use that in the refinement where the multiplicand need not be like 64-bit register, and similarly the ALU also doesn't require the 64-bit addition, because if you look at here each time the actual addition, if you look at here, the addition will take place only among the 4 bits only. So therefore we can use the optimally like the 4-bit ALU, like for example here 32-bit ALU and 32-bit multiplicand is sufficient and all. And so for that, if you try to optimize that, the optimized multiplier circuitry will be something looks like this. You can see here, because finally, because ultimately our product you will get as a 64-bit register. You get a 64-bit content, because when you multiply the 32 bits with another 32-bit number, it may generate a 64-bit. So therefore, the product requires 64 bits. So therefore, the product register should be 64-bit register. But the multiplicand and addition that need to be performed each time, that need not be 64-bit. That 32 bits are sufficient. Here, the way how do we do is that because instead of shifting the multiplicand towards right, you can shift the product towards left, towards right. Here each time the earlier the multiplicand is shifted towards left step by step, for every iteration. Instead of shifting the multiplicand, you can place the multiplicand static, but you shift the product and all. You shift the product in the opposite direction. That's what you can see in the, you can visualize here in this multiplication. Here, either way you can do it. Either you can shift the multiplicand each time towards this way, or otherwise keep a multiplicand static, and then whatever the product is there, because we are adding a product, intermediate products with this multiplicand and all. So you can add this product with the multiplicand, where the multiplicand will be, let it be static, and you just shift the product towards right side and all every time. So that way the same thing happens. And so in that case, if you use that particular technique where you don't need the multiplicand and ALU with the 64-bit registers and all. And you can also optimize. The multiplier need not have a separate register is not required. Multiplier need not have a separate register is required, because initially you have 64 bits product register is there. So in that you can initially it will be placed all zeros, but since it is a 32-bit addition, so we have to use only these 32 bits only, right? So therefore the lower 32 bits of a product register initially, let it be initialized, or let it be keep the multiplier over here and all. Keep the multiplier in this lower portion of the 64-bit register, and then you shift left each time, because the product has to be shifted left each time. So whenever you shift left, you can able to, one digit will be come out of that digit will be used to take the control action and all. That digit used to be take the control action, right? Because you have to check each multiplier digit and all, and based on that whether the addition has to be performed or not, so that you can able to decide based on that. So therefore, initially here in this optimized version, the multiplier will be placed in the lower side of the 64-bit register, and then the other portion will be filled with zeros initially, and later on the product will be, you will get the successive products by adding the multiplicand. You add a multiplicand and then shift this product towards left, towards right each time. And with that, when you shift towards right, then you will get the multiplier with whatever the least significant bit position that will be come out, and then you can able to check that one whether it's a 0 or 1. So based on that, here the ALU can be controlled, and you can able to perform the product shift can be done. So this way you can able to perform the multiplier using the internally ALU and the other registers and all. But here to support this 64-bit product, keep the product. So the MIPS will make use of the pair of registers known to be HL pair, high and low, named as like high and low. So those two registers will hold these 64 bits and all. Will hold these 64 bits. So here, if you look at here, strictly speaking, for every iteration, it requires the 3 operations, right? Earlier, actually, if you go by this way, it requires the 3 operations and all. That means the multiplicand has to be shifted, addition has to be performed, and then the result will be placed in the product register and all, right? And here the multiplier has to be shifted. So there should be 3 operations are required. So see that if it is 32 bits, 32 iterations has to be required. And each operation, suppose if it is happened in one cycle, right? So therefore, totally about 100 cycles are required if you go by these the original this method and all. And whereas, for example, if you can able to somehow keep all these 3 steps in parallel, if you can able to do that, for example, then in that case also you need to have like 32 cycles are required, right? 32, 33 cycles are required. And this is by using single like ALU and all. Suppose, for example, now the like you can have the high density chips are available, and the hardware becomes available, abundant hardware is available. So with that, suppose if you use a multiple adders, for example, because what we are doing here based on the multiplier digit and all, you are keep on adding the multiplicand like to the intermediate the products intermediate results one by one and all. So here, instead of doing step by step in an iterative way, so if we have like a provision of 32-bit ALUs, 32-bit adders, like such 32-bit adders, like we have some 32 adders are available. So in that case, you can able to perform all of them put together simultaneously, like because we know the whatever the multiplier digits are there. So that multiplier digit based on the multiplier digit, this one of the inputs of the 32-bit adders can be given. And likewise, you can keep these 32 adders in a sequentially, like start with the 0th bit, then the next adder will be in the first position. So the taking care of one bit, and then second bit, third bit. Likewise, if you keep the adders in a sequential way, and you can able to carry out the multiplication in the all put all bits together and all. So even then also you need to have the a delay of propagating the result across this 32-bit ALUs is required. And that means whatever the delay that is required for a one adder, that should be multiplied by the 32 adders put together. So that is the minimum delay that is required if you use the like even though if you employ the 32 adders, one put them in a sequential way also, you can have that much delay is required and all, right? And yeah, you can but you can able to do it in optimal way instead of keeping the adders in a sequential way. And we have techniques like you need not to percolate the like, but even then you need to add all these intermediate products and all, right? So but instead actually you can use some technique, an optimal way of adding these products in a parallel way using this particular circuitry. Suppose this is for a 32-bit multiplication, right? In that case, what you are doing here, you are keeping the adders, you are arranging the adders such a way that in a hierarchical way, where for 32 bits, for initially performing these 32 bits, you have this initially the 16 adders will be placed over here. And for each adder will take a two inputs. So therefore, you have a 32-bit adder, 32-bit multiplication means, so this will take two inputs like multiplier 0 bit multiplied by multiplicand, multiplier 1 bit multiplied by multiplicand. So this adder. So likewise, to take care of the 32 bits, you have 16 adders are required here. And in the next level here, we'll take the capture the outcomes of these two and then again further add it. So this here require eight of them. And again, outcome of these eights will be captured by four of them. So likewise, if you arrange them in a hierarchical way, and the way you can tap the outputs like this way, you can see here. Here it will from this the final adder will give you the bits 32 bits output, and those 32 bits output will be the middle of the middle of the 64 bits, and the remaining 64 bits remaining 32 bits can be generated from the initial tapped points like 16 over here and 16 over here. So that way you will get outcome of total 64-bit result of multiplier can be generated by keeping the adders in this way in a hierarchical tree structure. And with this, actually here, the delay can be very much reduced. Earlier, as I mentioned, even though you have a 32 adders, if you put in a sequential way, the delay that is required will be the propagation time, or like suppose whatever the adder will take the amount of time for performing addition. So that is multiplied by 32 is required. Like for example, adder requires 5 nanoseconds, for example. So there are 32 adders that all addition has to be done like one after another kind of a thing. So therefore 32 into 5 nanoseconds that is required in case of the earlier one. Whereas here, if you arrange them in a properly in a this hierarchical way, where these 32 adders will be placed in a tree structure 16, 8, 4, then 2, then 1, something like that. So in that case here, so since it is 32-bit addition, if you place it in this way, then the number of levels will be 5 levels will be there, like log n to base 2. That many levels are required. So since it is 32-bit addition, you need to have 5 levels of the additions are required. So therefore, with this, by using this arrangement, you can have the delay will be reduced to 5 times the adder delay and all, right? So that way you can able to like still even the faster the multipliers also can be realized by using the additional hardware and all, right? And yeah, then coming to the like suppose coming to sign multiplication, and also that can be done in a direct way. Like in case of sign, suppose if the multiplier and multiplicand have the different signs, for example, to take care about sign multiplication. So in that case, what you can do is that remove the sign bit away from that, and then the remaining multiplication can be carried out. And then based on the like if the polarities are different, Then you place the sign or keep the sign at the end after the entire product has been generated and all. So these are the instructions that are used by the MIPS for taking care of the multiplication process. And note that actually these multiplication instructions, so all these are like these are the pseudo instructions. That means the multiply the actual hardware will not perform this multiplication directly. The actual hardware will perform this multiplication using the adder circuits, shifter, and used based on those basic operations. But the compiler or the for the assembler, that means as when a person writing assembly language for his convenience, the compiler or the system will provide these pseudo instructions. These are like appears to be like a symbolic or assembly instruction, but this instruction will not perform or will not be implemented directly by the hardware and all. This instruction is again resolved into the several instructions using the simple arithmetic instructions. So at the end, you can able to get the final result of this one. But for the simplification process for the compiler and in the assembly language, we represent the multiplication as a single instruction like mult rs comma rt. Here rs and rt holds the one of them holds the multiplier, other will be the multiplicand, right? And this is the like signed multiplication. If you are not we are not giving any specifying that one. And suppose unsigned multiplication, the corresponding statement will be multi-u, where rs and rt each holds the like multiplier or multiplicand, right? And then after multiplication, we know that since it is a 32-bit multiplication, the result will be 64-bit. And the result will be result will be placed in the register pair known to be high and low, where the high register will keep the higher 32 bits and low register place the lower 32 bits and all. And then using these particular statements like instructions, assembly instructions, where the result will be again shifted to the desired register and all. Like MF high, that means that is multi like move from high register. High means because HL pair I mentioned, move from high to the RD or move from low to the RD and all. Because the product will be 64 bits and the 64 bits will be held by the a pair of registers high and low, and the low contains the lower 32 bits, high contains the higher 32 bits. And using these registers, we can able to shift the contents to the desired registers and all. And there is a register. There is another statement like mul rd rs rt is like R format instruction, and where here in this rs and rt contains the multiplicand and multiplier, right? And the result will be placed in the RD. But again, this register is 32-bit register. So therefore, ultimately, we'll get the result will be a 64-bit register, 64-bit, which will be maintained by pair of registers, high and low. But here in this particular statement, it just ignores the higher 32 bits. It just places the lower portion of the 32 bit will be placed in the RD and all. RD and all. Suppose if the result is more than that, just simply ignores or just simply it doesn't bother. It just want to see the last 32 bits of the least 32 bits of the product and all. Right. And here in this process, usually in case of multiplication and all, you will get an overflow, but to check the overflow and all, you can check the higher 32 bits and all. And sometimes even you require the overflow because even the 64 bits may not be sufficient. You need to have another bit that is required, because when you are adding these the result intermediate results and all, you will get the overflow may occur. That means the carry out may generate and all. So those things will be for taking care of that one. You need to have the other one more bit is required in principle. So this is the way the multiplication will be carried out in the processor and all. It's basically that it uses the arithmetic circuitry and like replication of that one if you want to do the faster multiplication, and so that way you can able to generate the multiplication can be carried out. So the next one is the division. So here the way we perform the division in a normal, like with a pen and paper, will be this way, as all of us are familiar. And in the division, we have these the terminology related to division will be like we have four terms. So a dividend, then the divisor, because the dividend is nothing but which used to be divided by a certain number. So that's known to be dividend. And a divisor is nothing but which used to divide is known to be that, but that number is known to be divisor and all. And when you're performing a division and all, you will get a coefficient, and as a result of you will get a coefficient and a remainder. You will get two results you will get. So one is the coefficient and other is the remainder and all. Okay, and here the coefficient, remainder, division, divisor, these four are related by an expression. We all of us will know that, like dividend equals to that whatever the dividend equals to coefficient multiplied by divisor plus the remainder and all, plus the remainder. So that is the expression. With that, all these four parameters, all these four numbers are related and all. Dividend equals to like divisor multiplied by coefficient plus the remainder and all. So that way you can able to relate all these four terms and all. And when you're performing the division, you should be careful whether the divisor is should be a non-zero and all. If the divisor is 0, then it leads to the erroneous result. That means that it's a division by 0. In principle, it's infinite. You cannot perform a division and all. So therefore, before going for a division, you need to check what is the value, what is the divisor and all, whether it's a 0 or not, right? And this is a normal method of performing a division known to be long division and all. So how you are doing that one? So this is your dividend, right? And this is the divisor, and you need to check that one whether the divisor is will be less than the this portion of the dividend or not. This portion of dividend or not. And so that way we'll check it out each time. And then how do you check that one? You just perform subtraction, and then afterwards whatever the number you will get, this number whatever you will get, so that will be we'll check that whether the divisor is more than this number or not. If it is more, then you just bring the other digits also. It so that it will be sufficient enough that the divisor can be again can be subtracted from the other the remaining portion and all. So that way we'll perform the division using the pen and paper and all, right? And here this we do it in a conventional way, but we want to do it by a machine. We'll try to follow the similar approach, but here we'll see that actually when you're performing a division, we'll come to know that whether the after this whether this will be less than the divisor or not. So these things and all, as a human, by having the practice and all, we'll come to know that. But as a machine, if you want to do that, we need to perform a subtraction each time. And then based on the subtraction, we'll come to know that whether based on the result, we'll come to know that sign of the result and all, we'll come to know that whether the divisor can be subtracted or not, right? So that way here in the division is not as straightforward as in the process of the multiplication, because in the case of multiplication, we are seeing that suppose we want to perform 32 multiplication, and we need to perform the 32 iterations in the same way, like based on the multiplier digit. So we need to see that whether each time the multiplier digit is multiplied with the multiplicand, and whatever the multiplicand will get, that multiplicand will be added in a appropriately shifted way, so that you will get a final result directly. But whereas in case of division, you need to subtract. So while subtracting, we have to see that from where you are subtracting from that, whether the divisor is like smaller than that or not. So these things has to be checked. And for that, we need to perform the subtraction. And based on the result of the subtraction, we need to perform whether the division can be subtracted, or we need to wait, or you have to do, you have to again restore, and again you have to do something, right? So this one can be, this is the flow chart, or you can say the sequence of steps that are involved in the division process and all, the division process. So if you start at the beginning, you can see the first step will be subtract the divisor register from the remainder, from the this one, the remainder, because the remainder register Here you can see this is the hardware that is required. Here the reminder will be a register having the 64 bit, and again the ALU is also 64 bit is required, and again the divisor also. Actual divisor is 32 bit, but you keep it like in a 64 bit register, because if you look at here in the conventional thing, each time you are just shifting the divisor. You can see that here the divisor is placed here over here in the rightmost or in this one, where the dividend is like this, and then in the you can say the leftmost bits of the dividend will be aligned with the divisor, and afterward the divisor will be shifted, like the divisor will be, you are keep on shifting the divisor and all each time, and then we'll see that whether the divisor is less than the this intermediate the subtract output or not. So that way each time the divisor is shifting towards right. So therefore, to accommodate all the shifts of the divisor, so we had to place the divisor in the 64-bit register, right? And again here initially the dividend will be placed in the remainder register, because you can see that here you have a dividend, and then you are keep on subtracting the divisor from the dividend, and finally you come to a stage where the dividend will be reached to the at the end, right? And then there is no more, the divisor cannot be subtracted or cannot be subtracted from the remainder from this the last the remaining portion of the dividend and all. So therefore here what you can see here, every time you are subtracting, and therefore that means these remainder we obtained from the dividend from the successive subtractions of the divisor and all. So therefore the initially will place the dividend in the remainder register, and then the divisor over here and all, and then the 64-bit ALU will perform the like subtractions and all, because we are removing that means we are subtracting the division from the dividend, and then we'll see the result, and based on that we'll try to update. So therefore here in the first step will be the divisor will be subtracted from from the this one, remainder is nothing but from the dividend, and then we'll see the remainder. That means here whatever is left, that means in the first subtraction we'll see that whether the remainder is positive or negative. If the remainder is positive, if the remainder is positive, then it means that when you're performing a division, the divisor is smaller than the dividend. That means the number of bits that are present in the dividend, it's smaller than that one, because you got the remainder is positive. So therefore you need to incorporate that means you need to incorporate or you need to place the one in the quotient register. You need to place the one in the quotient register, because the subtractor because the divisor is properly going through the dividend. That means when you subtract that, you are getting a positive remainder. It means that so therefore so you need to place the bit 1 in the quotient and all. You need to place the bit 1 in the quotient. Otherwise, for example, if the remainder is less than 0, if the remainder is less than 0, that means when you try to subtract the division, you are getting less than 0. It means that you are getting negative. So it means the divisor is more than that. Divisor is more than that one. So in that case, what you need to do, you have to shift the divisor by 1 bit. You have to shift the divisor right by 1 bit. So after that, actually, when you're getting, sorry, when you're getting negative, then you don't perform the subtraction. Again, you had to come back. Then you need to restore the remainder. Restore the this one. What do you say? The restore the dividend again. So that's why if you look at here in this, for example, here it's a positive, right? You are getting quotient will be 1 here and all. Then afterwards, if you look at here, after you subtraction, what you result, you will get a 1 0. You will get the 1 0. But this one, this is 1 0. And then what you do, you just shift the divisor by left once. When you shift the divisor by once, actually here what happens, this is 1 0, but this 1 0 and then this here it will be 1 0 0 0. So when you try to subtract that one, you will get a negative. It means that the whatever the dividend we are considering, so that will be less than the divisor and all. So therefore we don't want that. So therefore again, whatever the again we have to restore the dividend. That means we need to place again one more digit to support the division. So therefore, instead of 10, then we bring the one more digit to this dividend. So this is nothing but actually here. First of all, we are restoring the this one, the dividend, and then we are shifting the this division by one more bit. So when you shift this by one more bit, again here the dividend we are considering is 101, but the division is 1 followed by 000. But still again the division is more than the dividend. So that you can just check it out by the subtraction. When you subtract, you will get a negative. It means that this 101 is smaller than the 100. So therefore, again we had to then again we had to restore the dividend, and then we need to consider the next bit also like 1010. So then now at that time now you check the division. So now when you perform a division, you will get a positive one. So it means that now the division is smaller than the bits that are considered for division. So now positive. So therefore now we add the like you include one over here. So you can see the quotient. First we are placing one here because the divisor is smaller than the these 4 bits of dividend, right? And afterwards the result will be 10 because 10 means strictly it's like 0010, right? 0010 is smaller than the 100. So therefore you push 0 into the coefficient and then shift. Each time the coefficient will be shifted for every try. And then afterwards now again you will consider the one more bit of a dividend. So it's a 101 and it is still smaller than the divisor. So again you push 0 because it's smaller. So you push 0 into the coefficient and again shift it. And again now you just bring one more bit 1010. And now when you check that whether division is smaller than or not, now the division is now smaller. So now you place 1 over here and now you get the remainder 1. So there is no more bits in the dividend and all to bring it. So this is 10 is just smaller than the division. So therefore this becomes a final remainder and all. Or otherwise this shift of this division will be takes place about again to until it reaches the last point. And after there is no further shifts are required and all. So this process will be implemented by using this flow chart and all. And this flow chart or the sequence of the steps in this flow chart are realized using this particular circuitry. So here what we are doing here is that you can see here initially as I mentioned that here you have a like the dividend will be there. The dividend will be placed in the remainder, right? And then here we have a division. The division will be placed in the most significant position or in the like you can say that leftmost position and all, right? The division will be placed in leftmost position. Then you perform a subtraction. Then you perform the subtraction. So when you perform the subtraction, suppose if you get a positive, so it means that the divisor is smaller than the considered bits. So therefore you just insert 1 in the coefficient. And then afterwards again you shift the divisor by like left once. And then you perform the subtraction. If you get a negative, then you just push 0 into the quotient. And again you shift the 0 into the quotient and the remainder, since you get a negative, then the remainder will be again updated. Updated means again whatever the negative will get, so that negative will be added to the again you have to restore the remainder and all. That means whatever the original value is there, that has to be restored. So that way the remainder, whenever you will get the negative sign, the remainder has to be restored because it means that the considered number of bits in the dividend, they are not sufficient because the divisor is more than the value of the dividend. So therefore again you have to consider the next bit and all, next bit. So for that what you are doing, instead of shifting this, instead of bringing this bit here, what you are doing, we are shifting the divisor towards left so that the divisor now covers the next bit of the dividend and all. So that way here you can see here, instead of bringing these digits here, what we are doing here, we are just shifting the divisor like bit by bit towards left so that the divisor now covers the desired bits of the dividend. You see that first initially the divisor covers the 4 bits. Then afterwards we are shifting the divisor by one bit. So now what happens, the bits that are overlapping the divisor will be 0010 and then this 1000. When you look at that, when you see this, whether this is greater than this one or not, you perform a subtraction. When you perform a subtraction, you will get a negative. It means that the divisor is more than the considered dividend portion and all. So therefore again you shift the divisor by one more and now you'll get a 101. That is, now you are considering 0101. That is the dividend portion. And your divisor will be 0, 1, 1, 0, 0, 0. And again perform a subtraction. Again you'll get a negative. So it means that the considered portion of dividend is still smaller. So therefore, whenever you feel the dividend portion is still smaller, you place a 0 because you are not subtracting, right? And so therefore, finally, when you get a 1, 0, 1, 0, at that time, the divisor appears to be smaller. Then you place 1 over here. And by that time, the divisor also reached to the end. So therefore, there is no more revisions are required. There is no more shifts are required. And whatever the final content of the remainder, so that will be your remainder and coefficient will be the updated as per this one. So that way, this particular circuitry will perform the division in a conventional way, the way you have done. But here also, if you look at here, the same analogy, the way the multiplier used, here also, while subtracting, we are performing the subtraction with only 4 bits, right? We are not considering the entire 64 bits of this 64 bits of this one. We are just performing the subtraction only between these 4 bits. You can see here, even though we are considering the 8 bits here and all, but here we just performing the subtraction only over these 4 bits, right? And likewise, every time also we are performing subtraction only the 4 bits. So therefore, by considering those issues, you can further refine the circuitry where the divisor also don't require the 64 bits. You can have division of 32 bits is sufficient. And similarly, here each time you are performing a subtraction or addition only with the 32 bits. So the 32 bit ALU is required. But here initially you have to place the coefficient, dividend. So you place the dividend over here, and here you place the dividend over here, and so that way here the thing is that when you perform optimization, you have to place the divisor to be in the same position static, because you see that the corresponding circuitry is this one. Like divisor is only 32 bits, right? So the divisor we are not shifting at all. So in place of shifting the divisor, we are shifting the remainder and all. We are shifting the remainder. That means either way you can do it here. You can see here, either you can shift the divisor this way or otherwise keep the divisor in the same position. Shift the remainder, shift the dividend in the other opposite direction. Shift the remainder in the remainder means we are placing this dividend in the remainder register, so that's why you are saying. So these can be shifted in the opposite direction. That can be done, right? So for optimization case, we are doing that one, right? So you place the dividend over here first in the remainder register. Then afterwards, every time you shift the remainder towards left, Whereas earlier actually we shifted the divisor towards right. Sorry. We shifted the divisor towards right here. And to fix the divisor here without shifting, what we need to do, you have to do the opposite. That means the dividend we have to be shifted towards the other opposite direction, towards left and down. And when you're shifting this remainder towards left, each time 1 bit will be go off. So therefore, we need not have a separate coefficient register is required and all. You can use this remainder that 64 bits itself for maintaining the coefficient also, because for every shift, whatever iteration, you need to place whether it's a 0 or 1 has to be placed based on the sign of the subtraction, right? So therefore, first initially the entire 64 bits can be placed by the dividend, and then the dividend has to be shifted for every iteration. So in every shift actually, so you will get some vacant bit over here. So that vacant bit can be filled up with the desired value of a coefficient and all. So that way, using this optimized circuitry, you can able to perform a division. And if you look at here, the circuitry for division and the multiplier optimal one remains same. Both are same. But there we are performing addition, but here we are performing the subtraction and all. And you can see here, yeah, this particular table here, whatever is showing here, this is just the illustration of how you perform a division by a machine using a conventional way, using the way whatever I have mentioned, using the 64-bit this thing. So since it is a 4-bit division we are performing, so therefore the number of iterations that are required will be like 5 iterations are required. 5 iterations are required. If you look at here, if it is a 32-bit division, you need to have some 33 repetitions are required. You have to check whether the repetition is 33 or not, right? 33 or not. Because if you look at here, you see here, like if it is an 8-bit one, for example, right? you are placing here, this is the first iteration, 0th iteration, then go on. Like finally, this entire 4 bits has to be placed in the last 4 bits. That means here in this end. So that requires the 4 shifts, and then the initial one is there. That is the first one. So total 5 shifts are like 5 iterations are required in case of 4-bit division. The same way for 32 bits, you have 33 repetitions are required. Right? Right there, that's what. And then you can do the faster division. But whereas in case of multiplication, we do the faster multiplication since by arranging the adders in a tree structure kind of a thing. There is no dilemma. You had to perform additions only, right? There is nothing. But here, in case of division, you need to check that whether the divisor is smaller than that or not. So for that, we are doing a subtraction. Then we are checking the sign. If it is not sufficient, then you are shifting or bringing the another digit from the dividend. So these things are we are doing that. So for that, actually, it's not very straightforward to reduce the complexity, but there are ways, methods to introduce the quotient bits, because here in the normal process, we are introducing quotient bits one by one. You are just checking each time whether the divisor is smaller or not, whether divisor is small. If it is not smaller, then place 0 into that, into the quotient. If it is smaller, then place 1 into that. So that way the quotient bits are updated like one by one. So therefore, there are minimum 32 times are required. But here there are some methods by using some lookup tables where you need not you can place the quotient bits multiple bits at a time instead of one bit, and you can put sometimes 4 bits at a time. And when you're doing that one, sometimes you may do the mistake. You can your prediction may be wrong. At that time, again, you need to do that, redo the steps to take care about the misprediction and all. So therefore, by using some prediction methodologies, you can enter the multiple quotient bits instead of one bit and all. So that way the division time can be reduced to some extent and all. Right. So that way you can able to perform faster division. And these are the same, similar MIPS instructions will be there for performing a division also. Right. And here also we require a 64-bit register. And finally, at the end of the division, you have the higher portion of the 64-bit register contains the remainder, and the lower portion of 64-bit register contains the quotient and all. Because we are introducing quotient bit one by one in each iteration. So finally, at the end, you will get the lower 32 bits indicate the quotient, and the higher 32 bits indicate the remainder and all. And these are the instructions. They're not the actual machine instructions. These are, you can say, that pseudo instructions, pseudo assembly instructions and all. And each instruction will be further splitted into the multiple instructions, which has to be carried out by simple addition and subtraction instructions and all. So with that, we completed this the overall view of the multiplier and divisor and all. And so basically it follows our conventional one, and you need to see that how the conventional way of pen and paper way of multiplier and divisor will be translated to into the machine instructions, where it can be implemented by using simple arithmetic operators and all. Okay. So we'll stop over here, and in the next class we'll start the next topic. Is an important one. It's a core part of the architecture, that is designing of this one, the processor and all. And so far we had seen some components of that one, which performs the basic operations and all. And now we need to control all these things. Some instruction need to perform addition, some instruction perform subtraction, some instruction perform some logical operation. So in that case, so how this processor will take care of that one, how to fetch the register arguments and fetch the memory. So all these things we'll try to discuss in the implementation of a processor or designing a processor and all. Yeah, we'll stop here at this point. Yeah. Okay, we'll stop here. And so those of you have a next class, so you may leave. Okay. Yeah. So any questions? Okay, then let me stop the recording.